my name is José Ignacio from Innova Tracers, and I'm going to summarize our work and the scope of this presentation. In our current context, in relation to the pandemic, we would like to improve this situation, setting two main goals: to contribute to risk reduction and to reactivate the economy in a sustainable way. Our goal is to use the most advanced technology to monitor in real time and predict the level of risk of people that can be calculated, taking into account their lifestyle, visits to the premises and the environmental conditions of such premises. This information helps to control security conditions within business, offices, offering mechanisms to make decisions based on data in a dynamic and adaptable way, and aims to help people to know their current and historical risk situation, and to take awareness of the decisions they must make to care for others and themselves.
With these goals in mind, we propose to construct a system whose principal features and benefits will be introduced in first place, and after that we will explain a high-level approach to the methodology to develop this solution. Our main goal is to help people to take care of themselves and others, and contribute to improve the security of premises in general, obtaining and processing several sources of data related with person and environment and conditions. In the time we are living of COVID and future pandemics, there is a need for accurate and data-driven decisions based on dynamic policies and regulations regarding the risk of infection. These decisions have to take into account local and global sources of information, so the need of a centralized system arises naturally. For example, imagine you want to introduce a back-to-office strategy inside your company. Right now, all decisions are based on government global regulations of the region. Such generic regulations doesn't take into account current data about the condition of the premises and the persons who are interacted at each moment inside these premises. Information about sanitary conditions, the current risk per individual taking into account his or her interactions, and lifestyle outside the office should be taken into account. We propose to enable people in general and the managers of the premises in particular with tools to take proper decisions based on current data gathered from multiple sources. So we need to centralize this data to combine them in a unique system, and afterwards inform every registered user of the application using an app. To assure security conditions in public premises and to inform people about their current risk status, we propose to create a system that centralizes the information gathered from multiple data sources related with people and with the premises, to monitor in real time the security conditions and forecast the level of risk of COVID-19 infection. In Innova, we propose a monitoring system to estimate the risk inside the premise, recovering in real time environmental parameters and taking into account the individuals that are currently interacting inside the premise, track their interaction inside the establishment, and properly estimate the risk of infection that can help to assess the security conditions of all the people and properly adjust the measures to prevent infections. The data sources could be IoT devices that recover environmental measures, personal data obtained through the register of the users, etc. We know that the goal of obtaining the necessary data to enrich the solution we propose is in some cases something that would have to be clearly defined and regulated, especially when we talk about personal data related with health condition. But we would like to propose a line of work that could be followed and continually improved with the incorporation of new and rich sources of data. Once the data have been processed, some alarms related with the condition of the premise and with the people number and the distance between them could be generated. This data can be used also to calculate a preliminary risk indicator for each individual. We would like to contribute to give people useful information that could help them to know in real time and with historical perspective what is their current level of risk. With this aim, we have to gather and centralize all available data about the people in order to store the history of visits and associated indicators that measure important events related with their interactions and environmental conditions. Potential customers of this system could be people in general that want to improve their own security and help others to do it, clients, employees, whatever person with a mobile phone, subscribe or not to the service, companies that need their workers to go to the office, companies that want to establish a back-to-office strategy, and of course, businesses that want to establish real-time regulations of their workspace based on their customer risk. Some clear benefits of this solution could be help people to take proper decisions and to apply them in real-time safety measures based on current data. In general, people would feel more comfortable by knowing that the premise has a data-driven policy than to create a safe and secure working environment. This system could also contribute to reduce the risk of infection by adjusted safety measures that help employees, clients, and people. Obviously, assuring proper conditions at premises can contribute to a sustainable economic reactivation.
The methodology to develop the proposed monitoring system consists of 3 phases. On the first one, the system will collect information from multiple devices and different sources to create important variables to estimate a preliminary individual risk of infection. Once enough data is collected, the second phase consists on the estimation of a collective risk based on the interaction of the users. Finally, on the third phase, information of the preliminary individual risk and collective risk of the past 2 weeks is combined with the actual interaction of the individual and the room safety measures. The phase 1 is divided in 3 parts: the input data, the calculated variables, and the output. Regarding the input data, for this initial development, we use the indoor positioning and tracking of individuals, the air quality and ventilation of the premises, and restrictions and limits regarding air quality and capacity of the room, and the personal information survey to know more about the lifestyle of the individual. To obtain the indoor positioning and tracking, we thought to use a non-invasive method that doesn't require a specific hardware for implementation. So we use the Wi-Fi strength signal from the routers to identify the latitude and longitude of the individual, as well as the room, floor, and building, as long as the network is from the same client. To transform from the Wi-Fi strength signal to the latitude and longitude, a machine learning model is used, which is trained using the relation between the signal and the location. The implementation was performed in SAS Bayer, where several models compete against each other, including linear regression, neural networks, and gradient boosting. Regarding the air quality conditions of the room, different IoT devices with different sensors can be used to extract key information, for example, the CO2 concentration. For the restrictions and limit of the room, the legislations of air door quality limits and the room capacity are used. And regarding the survey, initial information of the lifestyle is asked, which informs us about the risk the individual is exposed. For example, if he goes to the office for work, how often, if he uses public transportation, and so on. Once we have all the information gathered, a set of calculated variables is extracted, which includes several alarms, for example, if the capacity of the room is exceeded while the individual was there, or if the safety distance was respected, or if the CO2 concentration levels were above the regulation, and so on. And finally, with this set of calculated variables, a preliminary individual risk is estimated for each individual. This is calculated using a weighted sum where the weights are selected based on studies, surveys, and expert criteria. The output is normalized and categorized so we have a high, medium, and low individual risk. When enough historical data is collected, now the phase 2 can begin, which consists also on the same 3 parts: the data input, a set of calculated variables, and an output. The data input in this case consists on the preliminary individual risk calculated on phase 1 in addition with the user's interaction. To combine this information, the user's interactions are tracked for 2 weeks on the room or buildings where the system is deployed, and the interactions are monitored to extract new variables like the number of interactions with high-risk individuals or with medium-risk individuals. If information of possible infections among the users is available, this also can be included as key variables. Finally, the risk of interaction is estimated based on this key high risk or medium risk interaction during the establishment risk time. For the last phase, the objective is to estimate a risk of infection for each individual based on all the previous information obtained. So, to do this, we use the preliminary individual risk and the risk of interactions with the information available of the last 2 weeks, and combine it with the user actual interaction on that moment and the actual room safety conditions. All that information is processed and combined by a weighted sum and then normalized and categorized to obtain a 3-level risk of infection per individual, high, medium, or low. To present and visualize the results, a dashboard was developed in which information of the results of each phase is presented, which includes the different calculated risk, the condition of the room, the list of interactions, and the indoor position of the active users with their individual risk associated. The implementation that leads to the dashboard are a combination of Python and SAS Via, which some parts were developed in a standalone Python, like the processing of some variables. Other parts were developed by integrating SAS Via to Python, like the creation and competition of the models, and other parts were purely on SAS Via, like the visualization and the dashboard. With such information, it is possible to make data-driven decisions to prevent possible infection, leading to a more secure and safe environment.
To present some conclusions, we can say that the proposed monitoring system has several features that differentiate it from the existing COVID monitoring approaches. First, information from multiple sources, which implies combining and analyzing multiple risk factors. Accurate and precise, non-invasive indoor localization via Wi-Fi strength signals in a building processed by machine learning models. A centralized and scalable monitoring system, real-time monitoring and notifications for fast response. Historical analysis of the interaction of the user considering the individual risk of the user. An open architecture to include new sources of data, new data fusion and processing techniques, and new modeling and forecasting approaches. Dynamic response regarding security measures that come directly from the data associated to the multiple risk factors analyzed.